Hi everyone, can you hear me?
Yes, ma'am.
Okay. So, have you guys gone through this week's lectures? Can you see my screen?
Yes, ma'am. It's with
Okay. So, I'll go over a couple of questions which I planned for this week. So, last week we discussed separable filters, right? Separable kernels, where you can efficiently implement a convolution operation for certain filters. So, yeah, so based on that, by looking at this matrix, so what do you think? Is this a separable kernel? Anyone? So, what is the condition for identifying whether a kernel is separable?
it should be a rank one matrix.
Right. And what would be the determinant of such a matrix? So, how can you say anything about the determinant based on the rank? Uh, do any of you know how you can identify rank and determinant if at all you find eigenvalues of a matrix? So, is this separable kernel or not? Is this a rank 1
Yes.
matrix? So, what is an easy check for a rank 1 matrix? Like, at least for some simple matrices, you can tell it directly, right? By looking at it. Can one of you say?
All the rows are a constant multiple of a confusion row.
Here, right? If you can express any row as a as it is linearly dependent on something else, then it will be a rank 1. I mean, in this case, you can see second row, third row is just a multiple of the first row, right? This is just twice the first row, this is thrice the first row. So it is a rank 1 matrix. So what is the determinant of this matrix?
Zero.
0. So how do you say it is 0? By just looking at it.
Because you can apply some operations and make it only the first one, all the other rows become zero, and then the determinant becomes zero.
Then the determinant becomes 0. Right. So when is the determinant of a matrix non-zero? So if you know the rank of the matrix, can you say whether it is a non-zero, it has non-zero determinant or not? That's my question.
If the determinant is equal to the rank, maybe then we can say it is.
Determinant is
Sorry, the order of the matrix is not equal to the rank. Then we can say that the determinant is non-zero.
right. What is the order of a matrix?
Like generally, we talk about square matrices in this context. So the number
Yeah,
of
you
rows
can
or columns.
compute determinants for square matrices only, right? Yeah, so when it's a square matrix, and so rank can be computed for any matrix. Anyway, yeah. Uh, so what would be the rank of a rectangular matrix, as in non-square matrix? I mean, uh, I mean to ask what would be at the maximum value the rank can take for a non-square matrix. So suppose I have a 4 cross 7 matrix. So what can be the maximum rank for this matrix?
4.
4. Why is that so?
Like the minimum of a number of rows and columns.
That's the minimum of the right. And how are how is a rank determinant and eigenvalues related? So suppose you compute the eigenvalues of you know the eigenvalues of a matrix. Can you say something about its rank and determinant? So how many non-zero eigenvalues will be there for this matrix, you think? If you know that rank is 1, right? Okay. So the rank of a matrix is equal to the number of non-zero eigenvalues of a matrix. So suppose I know the eigenvalues of the matrix, I can determine what the rank is. So in this case, it would be, I think, 1 0 0 0 0. 5 eigenvalues, one is non-zero and the other 4 are 0. So the rank is 1. And the determinant is the product of eigenvalues. So eigenvalues actually give a lot of information about the matrix. So the determinant is 0 because the product I have 0 as I have 4 eigenvalues to be 0 in this case. So the determinant is 0. The determinant is non-zero only for a full rank matrix. Anyway, uh, yeah, so suppose I have this image, it's a simple a toy image. Suppose I have these values and I apply linear contrast stretching. So what would the pixel location at this corner be in that case? So I'll give a minute. Can someone calculate what do linear contrast stretch here? So it is given that it is a 4-bit grayscale image, right? So what are the values this image can take if it can only take 4-bit values, the minimum and maximum value in this image? Can someone tell me that?
0 to 15.
0 to 15, yeah. So how do you calculate the linear contrast edge? So this is how you do linear contrast edge, right? So in this given image, we identify the minimum and maximum value and do this I minus I min by I max minus I min. So this scales everything to the range 0 to 1. And what is the whole range the image can take? It is 0 to 15. But here the pixel values go only from 0 to 7, right? So I'm stretching these values which are in the range 0 to 7 to 0 to 15. So I'll stretch this to 0 to 15. And so what is the offset is the minimum value that the range can handle, which is 0 in this case. So this doesn't matter. Understood? Okay, good. So which of the following here is local, global and point operation on an image? So suppose I'm doing convolution with 3 cross 3 kernel. What kind of an operation is this? Is it a local operation? What is a local operation? It basically takes, when I'm calculating, I mean the outputs are given the pixel values, I'm doing some function and then I get an output at each pixel. So that function also requires some local intensities, like it takes as input the neighborhood and computes some value. In global, it requires to look at the whole image, like all the pixel values contribute to this operation and I get some value out. Point operation is where I operate on every single pixel independently. So now, yeah, based on this understanding, so what kind of an operation is a convolution with 3 cross 3 kernel?
Local operation.
Local, right? So I'm looking at that point and its 3 cross 3 neighborhood to compute my output, right? So it is a local operation. So what about cross correlation with a 1 cross 1 kernel?
Point operation.
Yeah, point operation. And Fourier transform?
Global operation.
Global, right? I'm going from one space to the other where I take into account the whole image. I'm looking, so in the Fourier transformed image, I get a sense of what kind of frequencies are present in the image. So it gives the information of the whole image. So it's a global operation. Sure product. Okay. I myself don't know what this means. So this is a one by one pixel by pixel multiplication of one image with another. So what kind of an operation would this be?
Point operation.
Point operation, yeah. And flipping the image upside down, or any kind of such transform, moving it
Global.
global, right? At, at a current location, I want to look at its mirror pixel and then get that value. So it takes into information. I mean, it requires the whole image information to compute the output. Yeah.
Then in the last question,
Huh?
flipping would be a point operation, right?
Which which one?
Flipping the image.
Not really, because at the current location, so like say at the corner, for the topmost corner, what is the pixel I would replace the topmost corner with? The bottommost one, right? When I'm flipping it upside down.
Yes.
So, I mean, usually point to point meaning you're performing some operation on that pixel. Like, I don't need the information of what other pixel's value is. But here I need to know what the pixel value is at a different location, right?
Yeah.
So, it needs the whole image information to compute what the flipped image looks like. So, that is why it's a global operation.
Okay, ma'am. Thank you.
It is basically what information is required to perform that operation defines what kind of an operation it is. Yeah. So you have come across all these terms, right? For doing contrast stretching, filtering, etc. So what kind of operation, like how would you map these elements? So what does histogram equalization do? So what would you map histogram equalization to here in the second set?
Contrast stretching.
Contrast stretching, right? That's about it. It does image enhancement, right? Where you're stretching the pixel values range from whatever it is to the whole spectrum of 0 to 255. So it is called. What about cross correlation?
Ma'am, it measures the similarities.
Hmm. So when you slightly move your image and then see how uh, similar it is with respect to its neighborhood, right? Something like that. So it's a local operation. And what does Gaussian kernel do? Gaussian kernel is a smoothing filter, right? It is a low pass filter. So suppose, so what does a high pass filter do when you apply to an image? It's just a random question. Like I have an input image. What kind of information? I mean, how would the output look when I pass it through a high pass filter? What does even high pass means in an image?
It will block the low frequency signal.
Yeah, that is what high pass filter means. But in the perspective of an image, what does it do to the image?
Highlight,
Hmm?
highlight, highlighting the corners or contrast something.
Mm-hmm. Kind of, but not exactly. Okay, what does low pass filter do? So Gaussian kernel is a low pass filter, which I've seen here, but so what does it do?
It blurs out the image, basically captures the color and context information.
Color and context.
Like, those are the low frequency components.
Yeah, that is true. It tries to retain such information, yeah. Basically, it tries to get rid of noise when I pass it through a low pass filter. Like the image would look a bit more smoothened. If you get to what. And a high pass filter is captures high pass components, right? What do high pass components mean in an image? Not in the frequency domain. Frequency domain, I know it is high frequency components. Like in the image space, what kind of things, characteristics represent high frequencies in image? What are high frequencies in an image?
Things like edges, corners, and
Right, edges, corners, right? Any change in intensities, like drastic change in intensities, correspond to high frequencies. So when I pass an image through a high pass filter, I will actually be detecting edges, right? So this week's lecture was primarily on edge detection, right? So how many of you are all aware? Are you all aware with SIFT? With what SIFT is? What does SIFT stand for? Okay, so none of you have gone through to this week's lecture, is it?
it is scale invariant feature transfer.
Scale invariant feature transform, right? So what does it do?
It tries to extract key points and also describe the key points in a bit robust way.
Right. Yeah. So SIFT is a key point descriptor. And why do we need to get key points? It can be used in variety of applications like image matching and then stitching of images, etc. Right? Like, so what do key points basically refers to some like extracting descriptive features of the image, something that is unique, kind of locations which together, put together, can describe what is present in the image. So if I can extract features in one image and I want to locate where such features exist in another image, I can get, if I can define the describe have descriptors for such key points, I can match them to the key points in the other image and get one-to-one mappings. So in all such, so SIFT is used in a lot of image applications. It is one of the seminal papers, which is a very good design, very well designed algorithm. So yeah, so this is one of the steps involved in the key point in the SIFT algorithm, where once I get the key points, and finally if I have to whether it is a good key point or not to get a measure of that, we compute the Hessian of this matrix at a particular key point, and then calculate this value trace square by determinant. If that is greater than a certain threshold, then you reject the key point. Okay, so suppose I have an image whose pixel values are represented in 4-bit 2's complement. I want to compute its negative image. So if these are the values, how would I compute its negative image? So what are the range of values that can be represented in 4-bit 2's complement? So I'll have one sign bit and the other 3 bits to represent the number, right? So the values can go from -8 to 7. So because the values can go from -8 to 7, and if I have to compute its negative, I just need to use this mapping, right? If it is 7, then my negative goes to maps to -8. If it is 6, it maps to -7, and so on. 0 maps to -1. So I thought of going over the code for, like there are 2 notebooks which I thought I'll go through. So how many of you are understand what canny edge detection means? Do you want me to quickly go over the method and then the code, or can I directly go over the code? What do you want me to do? Because most of you didn't know what it just mean and high pass, low pass, so that's why I'm asking.
Yes, ma'am. Can you first go through the method?
Okay, fine. I'll quickly review the lecture content and then we'll go to the notebook. Okay. You can see the my screen, right?
Yes, ma'am.
Yes, sir.
Okay. So to briefly say, how do you define what edges are? Anywhere where there is a change in intensity, we call it an edge, right? Like I go from so I have a plain white image and suddenly I have a black line, that is a change in intensity, so that refers to an edge. So here, if this is how like a small patch in an image look, so these two actually, this shows how the pixel values are changing along the line, right? So what does this curve here represent? Can someone interpret this for me? So here the values are high, right? So suppose the pixel values are in the range 0 to 1. So here it is white in this region. So that's why it's at a high. And then it drops to 0. So it drops to 0. And again, once the black part is over, again I have white. So it's that this is the intensity profile of an edge here. So how do I detect where an edge is? It's like what I want to measure is the rate of change of intensity, right? So if I compute the first derivative of this, it would look like this, right? So if I have an image, if I compute its derivative, the derivative of the image, then wherever I have peaks in the first derivative, those regions correspond to edges. Does that make sense? Like, I want you to understand what edge means so that you know how you define or like design edge detection methods. So in this image you can see, right? So in the first one it goes from black to white and then white to black or gray or whatever. In the second one you're going from gray to black and then gray. So how does the intensity profile look? Here it goes from 0 to 1 to 0, and the second case 1 to 0 to 0, but both are edges, right, in this case and in either case. So when I compute the first derivative, here I have a peak which has a positive value, and when it drops down from like white to black, then the change is negative, right? So the peak I have a negative value, so that's the first derivative. But then both the values, I mean like both the peaks correspond to edges, right? So that is why we compute second derivative. So when I compute second derivative, I have positive yeah, so this is how the second derivative would look like, right? At this point the second derivative is 0, it's a peak, so it is 0. And again the value is slowly decreasing. I mean the slope is decreasing here, right? So it goes this way. So anywhere there is how do I say, like these kind of zero crossings correspond to edges in an image. Okay, someone has a question, is it? You can
Yes, ma'am, I have a question.
yeah, you can unmute and ask in case I don't.
Ma'am, why we are increasing the intensity of this image?
Oh, it's just an example. Like, suppose some region in an image looks like this. This is an edge, right? So how do you detect it? This is how edges are defined. It's a demo, like a toy example to show you what an edge means.
Okay, ma'am.
Okay, so I have an image which will have lots of such things, right? It is a very simplistic example. So anywhere I see these kind of this kind of characteristics, right, where your first derivative has peaks, those kind of regions correspond to edges. That's what I'm trying to explain. So how do you compute these derivatives? So in what is a derivative? It's the rate of change of function, right? So this is what a derivative is. If f is the function, in this case what is our function? The intensity values are the function. So I want to measure the rate of change of intensity values. Because I have pixel data at discrete locations, we compute like the difference of it. So if at a particular location I want to measure the rate of change, is I just take the value next to the value of the pixel next to x and find the difference. So the delta x is 1 because I'm measuring the rate of change at 1 pixel level, right? So it is 1. So I calculate this, and by calculating this I'll see if there is a change in a horizontal direction, right? Because I'm measuring across x. And the same thing I can do for y, right? This is dou f by x of xy with respect to x direction. Can do the same thing in y direction, where the difference would be f of x comma y plus 1, which is the pixel above my current location, minus f of xy. That gives the difference in the vertical direction. So by doing this, I can compute horizontal edges and vertical edges, and then I square and sum them can give me a summary of the whole edges actually. So yeah, so this is how these images would look like. So this is the image, right? If I take what this is, like I put this filter at the current location, that is plus 1, meaning f of x plus 1 minus the current location. It gives me this. So what kind of edges does this show? How the intensity changes when I scan, like if I go from along the x direction, right? So wherever an intensity changes along the x direction, see here there are these white and black stripes, right, in the sort of in a vertical thing. So I go this way and you can see these edges. So this one shows how the intensity changes in the vertical direction, right? So you can see edges here, like near the whiskers, right, where I have these stripes. You can see how it changes here. So this gives me horizontal and vertical filters. So there are, I mean, the same kind of these differences can be you can design different kind of matrices to compute the edges. Some common ones are the Sobel edge is a one common filter, where I take not just the current pixel and the next pixel, I take into account the whole neighborhood. That is, I take the left pixel, right pixel, and even the diagonal pixels into account to see if the pixels on the left side are higher than the pixels on the right side. Alright, if I do this, and it gives what? Oh yeah, it gives vertical edges, right? So yeah, this gives vertical edges. So this is how the output would be. Understood why this is a vertical edge? Similar to this, right? I'm going from left to right and I'm seeing where it changes. If there are vertical edges, I will check whether the left and right side have significant difference. If it is horizontal edges, I want to check if my top pixels and bottom pixels differ by a lot. So this gives this is vertical edges. Similarly, so this filter gives horizontal edges. So here I can see near the collar, right, like higher intensities here rather than here. And yeah, so there are different filters like Privet, Sobel, Roberts. All of them do edge detection, slightly differently designed ones. So primarily edge detection is basically computing the gradients of the image. So at a particular point, how would I define what it is? It like what the gradient is at a particular point. I calculate its change along x direction, its change along y direction, and this would be my gradient vector. Right. So in this case, I have change only along x-axis. In this case, I have change only along y-axis. Along x-axis, nothing changes, right? So dou f by dou x will be 0. But in this case, so it is dark here and light here. So my intensities are changing along both x direction and y direction in a uniform way. So that is why my gradient vector would be like this. Do you understand why these the gradient vectors point in these directions here?
Yeah, yes, ma'am.
Okay. If you have any doubts, I mean, like if you don't understand anything I'm explaining at any point, just stop me and ask. Okay. So this is how you would define the gradient direction, right? Theta is tan inverse of dou f by dou y by dou f by dou x. And how do you compute the strength of the gradient vector? Just calculate the magnitude of this this vector. So if you calculate the magnitude of that vector, okay, do they have an image, final image? Yeah, so this is how it would look like. This is the input image, this is the x derivative, y derivative, and I compute the magnitude by squaring, summing them, and taking the root. This would give me the gradient magnitude, where I see the edges, all the edges, right? Yeah, so how should I, um, so in an image I can have lots of very noisy spaces, right, where I mean, because if there is some noise in the image due to how it's captured or something, so all of those can actually contribute to these kind of differences, right, if it's not clean. So I would want to reject such like bad edges detected, or if there are this, right. So there are all so this is, yeah, this is called canny edge detector, where the first step, yeah, so one thing is I would want to ignore any noise that is present, uh, and the edge should be as close to, as in, to the true edge, and it should not be a very thick representation, like, yeah. So to do that they have like multiple steps. With the second step is, the first step is passing through a Sobel filter to get the edge map. Then they do something called non-maximal suppression. Yeah. So So what they check in non-maximal suppression is, so suppose this is how like my magnitude, like the gradient map would look like at the edge point, like, so wherever it has ones, so I take that point, I look at the gradient vector. So if this is how the gradient vector is, then I check its neighboring pixels along the gradient. That is because, so the gradient is in this direction, I'll check this pixel and this pixel, like, which are diagonally related to the pixel, right, and I'll check whether the values at those locations are lower than the value at the current location. If it is, then it is truly a gradient, and I retain such pixels. But if it is not, uh, then I would reject such locations. So this is called non-maximal suppression. So if there are very thick edges detected, which is unnecessary, it kind of gets rid of such points and gives out the true edges. So this is how the image would look before and after the non-maximal suppression. So after this is done, they do something called hysteresis thresholding. So suppose I have gotten rid of some edges at some point by doing this thresholding, then what they do is have two thresholds. One is a high threshold and one is a low threshold. So if the gradient magnitude is more than the high threshold, then we consider it is a true, like, significant edge, and you keep that point. If it is lower than the low threshold, then you reject such point. But if it is between the low and high threshold, they check if it is connected to an edge pixel, as in, so here you see that, like, the eye is not very clear in this image, but it is much clearer here, right? So because in non-maximal suppression it has gotten rid of some edge points. So what they see is not, if it lies between the low and high threshold, then they see if the neighboring one is actually a true edge. So if it is true edge, there is something connecting there, right? So you call that also as an edge, and you bring back some edge points. It's something like that. So after doing this, the hysteresis thresholding, this is how the image would look like, where you can see a lot of edges very clearly, right? So this is called the canny edge detector, where the first step is to filter the image using the derivative of Gaussian. So why Gaussian derivative? Basically, it's usually a derivative of an image. So one pre-processing step that is done is doing derivative of Gaussian, or like basically applying a smoothing filter, right? I pass an image through the smoothing filter so that I get rid of a lot of noise points, and then apply the derivative, or that's like the Sobel filter, Privet filter, one of the derivative filters. So I get the gradient magnitude and the orientation of the gradient also, right, when I'm computing the x past the x filter and the y filter. Then I do the non-maximal suppression to get rid of like thick edges. Then the last one is hysteresis thresholding to like connect any lost edges, like missing edges, by defining two thresholds, high and low. Yeah. So yeah, this is the whole pipeline. So given the original image, so first I smoothen it, and then I calculate the gradient magnitudes. So I kind of get an estimate of how the edges look like, but they are not very refined, right? So then I do non-maximal suppression, where whenever the edges are thick due to like say a slow change in intensity rather than a drastic change, so it gives me a thin line, as in basically just one pixel edge kind of thing after I do non-maximal suppression. Then double thresholding is basically getting rid of the low taking in the hysteresis. So identifying the pixels where the gradient magnitude is greater than high, and removing where it is lesser than the low. So I'll do that, and then edge tracking by hysteresis is where you connect the missing edges, and this is the final output. So yeah, these are some examples.
Ma'am, I have a question.
Yeah.
Ma'am, is this the same technique we used to build a monochromatic reels in 90s or 80s?
Monochromatic reels.
It's on that stores images for a very long time.
That would have the whole image content, right? Not just the edges.
Yeah.
That is different from this, right? Here I'm trying to only get edges.
Oh, okay, ma'am.
That is storing the originals, right? Not the edge part only. Okay, some factors that can affect how the results turn out in edge detector is the first step, where you were doing the Gaussian smoothing, right? So based on how much kernel size I have, I can get too many edges or less edges, very sparse ones. So if I use a bigger kernel, then I get like very distinctive edges like this. If I use a very small kernel, then I get very fine edges as well. Because if I'm using higher sigma, then I might have smoothened this kind of transitions here, right? So all these transitions are not captured here. But with smaller filters, even these transitions are captured, so I get all these lines. So based on the need, you can like tweak this to get what you want. So in some use cases, these kind of things can be noise. In some cases, you might need those edges. Okay, maybe I'll go over the so the notebook which does canny edge detection. Yeah, so all this is done on grayscale images, right? So in this part, okay, anyway, I'll just go over it. Yeah, so here, um, yeah, I read the input image and like get the three channels RGB, which correspond to channel 0, 1 and 2. Oh yeah, this is something you have to be mindful of. Which channels correspond to what? In PLT, yeah, PLT.im read, I think it is in RGB. If you use CV2 to read, it will be BGR. I think PIL reads it in RGB. So which corresponds to what depends on what library you are using to load the image. And so the grayscale is basically a linear combination of these three channels, and the weights are these are the weights. So yeah, there are even library functions, right? CV2 library, skimage, all these have functions that can convert RGB to grayscale images. So anyway, you get the grayscale image. So once you get the grayscale image, then you want to apply the Sobel operator. So this is what the Sobel operator. So horizontal kernel. So the horizontal kernel detects vertical edges, and the vertical kernel, that is GY, detects horizontal edges. Makes sense. You saw that tiger example, right? Why this detects vertical edges and this detects horizontal edges. Yeah, so define these filters are defined here. These are just defined as numpy arrays, and uh, yeah, so this Sobel filtered image. So I'm just creating a placeholder which is the same shape as the input image. So here we're doing the convolution operation. So I'm iterating over the rows and columns of the image. Why is it rows -2 and columns -2 here?
We have not padded the image.
We have
Not padded the image.
we have not padded the image. Yeah, that is fine. So why 2 here?
It's a 3x3 kernel.
It's a 3x3 kernel, right? So the last location I can go to is actually the number of rows -2 to perform this operation. So suppose it was a 5x5 kernel, what would it be?
-4.
-4, yeah. Yeah, so I am iterating over them. This is my local neighborhood around that pixel, right? Like at each location, I2, I+3. And so Gx and Gy are the kernels which I have. I multiply and sum them. So this is my gradient at x, the horizontal gradient, vertical gradient, and the magnitude image. So this is my gradient magnitude image, which is square root of gx square plus gy square. and I am visualizing it here. I don't know if you can see what, like, it is very mild here. Can barely see it, but yeah, it has kind of detected the edges. So yeah, I've done the first step, right? Okay, not really the first step. This is how we get the magnitude image. Anyway, in Canny edge detector, what is the first step? It is to filter the image with derivative of Gaussian. So yeah, so how do we define a Gaussian kernel? Suppose I want a 3x3 Gaussian kernel with sigma equal to 1, then so this is the function, right? E to the power minus x square by y square by 2 sigma square by into 1 by 2 pi sigma square. Yeah, based on the grid size I want, I compute this Gaussian kernel and I get the filter. So this is how the image looks like in the grayscale. Now I convolve this image with a Gaussian kernel of dimension 5, which gives me a smoothed image. So yeah, this is the smoothed image. Then I find the the derivative of this. So here I am, yeah, so basically in the first part what we did was we coded how exactly we are doing the like, we didn't use any library to apply the Sobel operation and get the derivatives, but yeah, here, yeah, we're defining what the Sobel filters are, and yeah, we are using the library to do the convolution. So this is my input image and I want to pass it to this kernel X and kernel Y, and I will get the horizontal gradient, vertical gradient image. Then I compute the magnitude of it, right, which is np dot hypotenuse, which gives ix square plus iy square, square root of that. And this is a contrast stretched image where I'm just scaling the gradients to the range 0 to 255. This is linear contrast stretch, right? Is it or not? Is this linear contrast stretch? This line? We saw that equation, right? Like I minus I min by I max by I min into the range, the maximum range. So G pi, its maximum value, into 255. So I'm doing linear contrast stretch of the gradient magnitude image, and then theta, this is the gradient vectors of the image, right? So I'm returning, the input is my smoothed image which I got after passing through the Gaussian kernel. Now I pass it through the Sobel filter and get my gradient magnitude map and the vector, like the direction vector. This is the magnitude map and this is the the vector. Yeah, and the next step is doing non-maximal separation. So in non-maximal separation, I want to see like I will look at the gradient vector, the angle of an edge, and then see along that edge if the neighbors. So if if the edge is the gradient vector says it's at 45 degree, then I will look at its right corner, like along the diagonal, the right one and the left one below, see whether the value of the pixels at those locations are smaller than the current location. So here you can divide the whole angles into different bins. So here we are dividing the whole 0 to 180 degree into 4 bins. So around angle 0, that is yeah, along the x-axis. So if my angle is between 0 to 255 and 157.5 to 180, yeah, if it is along the x-axis, close to the x-axis, then I will look at the right. So this is the right pixel, right, image of I comma j plus 1, and this is my left pixel. So I will keep the current edge pixel if only it is greater than my right pixel and left pixel. So if the angle is around 45 degree, so that's the bin. The bin is 22.5 to 67.5, which is centered at 45 degree. So at this I will look at I plus 1 and the yeah, this is the vertical left one, right, like so this is the left corner, and this is the right corner of in my neighborhood. So I look at them and check. So this is how I will compute what its neighborhood pixels are, and then I will check if my current value of the gradient map is greater than its neighborhood, like both q and r define its neighborhood points. So if only it is greater than this, then I will keep the edge, otherwise I'll make it 0. So by this I am getting rid of redundant edge points. Okay, this is actually a bad image to see things. Can't really see. Yeah, once I've done that, the last step is linking and thresholding, the hysteresis thresholding, right? So here for the image we defined two thresholds, low threshold, high threshold. So if the image is greater than high threshold, okay, this np dot where of image greater than high threshold returns me all the indexes, that's in the xy locations of all the points where the image is greater than high threshold, and zeros of ij, this returns all the locations where the image is lesser than low threshold. So at all the points where the image is greater than high threshold, I set it to strong, which is in the case here what the value 255. For all the weak points I set it to 25. Okay. Basically some low value, and then I return the result. So this is how it will look after my thresholding, where only I have retained only the strong edges. So the hysteresis part is where I am connecting the pixels. So what? Yeah, along with strong and weak, here I would have also identified which are the ones where I mean those intermediate regions, right, which lie between the low threshold and high threshold. Those are correspond to the weak edges, where I don't know. I might want to keep some and I might want to reject them. So all these are mapped to this value weak, and then I check. Okay, this is a mistake. This has to be 25 and this should be 255. So whatever you define as strong and weak here, right, the same value should go here. So if it is a weak pixel, I mean weak edge, that is something that lies between the high and low threshold, then I check its like its neighbors, that is its left neighbor, top neighbor, all how many other 1 2 3 4 5 6 7 8. So I check all its 8 neighbors, and if any of its neighbors is actually a strong edge, then I make it also a strong edge. But if none of them are is an edge, then I make it as 0. Did you understand what this does, what this function does? If you have any doubts, ask me. Okay. So if there were any connecting edges, so I would get back those after doing the hysteresis thresholding. So that is what Canny edge detector is about. So now I will go over the SIFT algorithm briefly and then the code. Yeah, so one main application where it is used is to identify if it is, I mean, the mapping of one image. If I've done a perspective transform and want to check if I have the same object in a different image. So if I can identify key points in one image, then I can check in the other image if I can find the corresponding key points. Then I found the object, right? It is, yeah, can be used as a naive object detector, right? So here some salient features of the image are identified, and I defined descriptors for each of these features. And in the second image, where the same toy is rotated and placed in a different location, right? So from this image also I identify its key points, and if I can find a matching descriptor, if I can find descriptors to match here, then we've identified the corresponding locations. So it can be used as I mean to search for an object or stitch images and so on. So it has these 4 key steps, which is scale space extrema detection, then key point localization, orientation estimation, and defining a key point descriptor. So the first step is to identify what are interesting points in an image, which are, so what are the key characteristics, I mean, which should define a key point is that it should be invariant to scale and orientation, right? So here whatever descriptors I get, I mean those points, um, so irrespective of like in a new image, the new image can be either scaled, rotated, any kind of perspective transform can be done, but the key points I identify should be invariant to all such transforms, right? uh, so yeah, that is a requirement of a key point. Yeah, so for the first step we do scale space extrema detection, that is, so have you guys do you guys know what Harris corner detector is? That was a previous method, right? Like which was one of the first methods called to do corner detection. But then Harris corner detection was not invariant to scale. So only if you have both the images at the exact same scale, then the key point matching can be done in Harris corner detector. So to avoid that, here they defined scale and orientation invariant key point, which is done using difference of Gaussians. So what is so first is I would construct a scale space, that is I will define Gaussians of different scales, like in the first, so this is the first scale, this is the second scale, and so on. So the first scale can detect like blobs which are of say approximately of, I mean the shape of it is of this order, and then the next scale slightly smaller key points, I mean smaller features, and so on. So I can define different scales, so I can define Gaussians at different scales and compute the difference of Gaussians. So why difference of Gaussians? So difference of Gaussians would help us detect blobs in an image, which are like corners where the intensity changes in all directions. So this is an efficient way of doing difference of Gaussian or like applying a Laplacian. So I compute the Gaussians in an image, compute the difference between two sigmas, like two corresponding sigmas, so that this gives me the DOG filters. So at each scale I compute the DOG filters. Yeah, so the difference of Gaussian is basically I apply the Gaussian at scale, I mean sigma, and its next one, which is some multiple of that, which is k sigma. So and then I compute the difference between them. So I have these DOG images. So once I have them, in this I want to identify whether a particular location is an interesting point or not. So for that, at each location I look at its neighborhood across scales, that is one at the top and the bottom one. So I look at this 9 cross 9 neighborhood, and if the value here is greater than all the values in its neighborhood or smaller than all the values in its neighborhood, then I call it as an extrema. So there are how many? There are 9 here on the top, 9 in the bottom, and 8 here, right? So 9 3 are 27 minus 1. So there are 26 pixels with and points which I am looking across the scales of images. So then I select a pixel only if it is larger or smaller than all the 26 pixels. So these points are called as extrema. So once I identify, but it would have identified a lot of such points. Then the next step is key point localization, where uh, so it So suppose I have detected some extrema, but then the exact location of that key point can be slightly off because of like this kind of discretization of filters. So to identify the exact extrema, they compute the Taylor series expansion of the scale space function, and then identify like, so I have this function, then I have these points, and based on these points I get the Taylor series expansion, as in basically a representation of this curve, and then identify where that curve attains its maxima, I mean like local maxima or minima. So this is the definition of that curve, and then to identify its exact location, I want to compute where it attains its maxima, right? So I do the differential of this and set it to 0 to identify the local maxima, and the exact location would be this you would get by setting the derivative of this, like dou d by dou s to be 0. So once you get this, you have identified what the key point, where the key points are. But again, yeah, it would have a lot of key points detected, but not all of them might be of our interest. So to get rid of some noisy key points, they use this function. Like I compute the Hessian of that matrix, I mean Hessian of that local neighborhood, and calculate its trace determinant, and evaluate this ratio, trace of that Hessian square by determinant of h, and if this is greater than a certain threshold, I reject those key points. So once you have got the exact location and gotten rid of unstable key points, the next thing is, so we want so the having the scale space function will make sure that the key points are robust to scale, but then I also want it to be robust to orientation. So that is why we estimate the orientation of these key points to achieve rotation invariance. So how do we get these the rotation invariance? So at every point, so suppose this is a key point detected, I will look at a neighborhood of this, say here for example a 8 cross 8 neighborhood, and each point I would compute the gradient directions. Then I compute a histogram of those gradient directions. So like, so I have my angles which can be in the range 0 to 2 pi, 0 to 180 degree, 0 to 360 degree, and 0 to 360 degree. I put them into 36 bins, like and get a histogram. So so I have 36 bins, and I put all these gradient vectors into one of these bins, right? And then see which is the bin I have that has the maximum direction, and I assign that direction to that key point. Makes sense? Anyone has any doubts on this orientation estimation? Yeah, so along the using the magnitude, they also use a Gaussian function so that the closer values to the key point are weight higher than the farther ones. So based on this, whichever bin has the peak, we assign that direction to that particular key point. So yeah, here as an example, if this is my original image, if I just identify the extrema, I would have found so many key points, but then yeah, I use that thresholding technique, right? Like using that Hessian based threshold computed to get rid of some noisy key points. So after that, I've also, I mean, estimated the orientation at all of them. Now I want to define each key point. That is, like something unique for each key point, so that I can use it to match it across images. So to do that, similar to the orientation, this right, in a similar way. So I take a neighborhood, for example 8x8 neighborhood, although originally it is done on a 16x window. So I take a neighborhood, and so I divide them into 4 bins like here, and within each bin I compute the I compute the histogram of the gradient. So that is how many gradients I have along this direction, and so on. Say I have put the whole thing into 8 bins, and see how many of them I have in each direction. So having those histograms in each of these uh, like 4x4 neighborhoods, so I get this whole the histogram, and I put together all 4 of them, and which defines the key point descriptor at that particular image. So it kind of defines at a particular location what kind of gradients I have in that kind of neighborhood, in the neighborhood. So this is unique to each key point, and so across images I can get these key point descriptors and see how similar these two vectors are. Yeah, so these are two images where these are the key points identified here and here, which are basically like some perspective transformed images, like just two viewpoints of the same region, uh, which can be matched using shift. Yeah, it can be used in image stitching applications. So you guys have all used the panorama view in the image in your phones, right? So a very naive way of doing that is I have to capture two images of a scene, but now I want to stitch them. So how do I stitch them? I identify the corresponding points. So like this peak is the same as this peak, right? So if I identify corresponding points in the two images, then based on where they are mapped to, like I merge the two images based on that. So these are the feature shift points the key points identified in both the images, and then based on the key point descriptor I can find the matching points. So this matches to this matches to this, and so on. So once you find the corresponding points, I can overlay the images, so that like the first image overlaid here, right, like it's slightly rotated here, so that the images match here. So that is how like shift is one of these the seminal works done in I think for 2001 or so. Any questions on what is the use of shift or anything? So I'll briefly go over this implementation of Swift. Um, so the first step in Swift is to detect the extrema, right? For which I want to compute the difference of Gaussian of images. So given an input image, I upsample and downsample the image, get the inputs at different scale, create the images, like basically create the image pyramid, which is the same image at different scales, and which I operate on different Gaussians, right? So So I take my input image, I apply it, I apply Gaussian filter to it. So I define the number of octaves in the image, that is how many at what scales, how many scales I want, and in each scale, how many as in Gaussians I would operate on in each octave. So if I choose a scale like say sigma and another sigma for the next octave, within each octave, suppose I choose I think here they've chosen 8 images per octave. So the sigma for each image within the octave is calculated in this way, as in square root of the previous sigma, current sigma square minus the previous sigma square. So once you define all the Gaussians, uh, you can get the whole octave. So it looks something like this here, where the same image operated using different sigmas within one octave. Then, like, how do I compute the DOG images? Where I take the images, the consecutive images in the DOG pyramid, and take the differences. So once I identify, get the whole DOG pyramid, the next step is where I want to identify it is a local maxima or minima, right? Where I will look at the whole neighborhood. So here, I will iterate over that whole image pyramid and take so 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 at so take one frame which is above and one frame which is below, so that those constitute the three images, the first, second and third image. And so I look at every pixel, I look at its neighborhood, right? Like it's the 26 neighbors, so which is the current pixel, like the left, right, the top one, bottom one, all of them. So not sure where they did the. So extrema detection part looks like I don't know exactly where. Oh yeah, here is the scale stress extrema detection. Yeah, so yeah, given the images, I mean the DOJ images, the first step is to find the scale space extrema, right? So here, I will go over all the pixels in the image, take the neighborhood like the first image, second image, third image around the pixel value ij, take it to cross neighborhood. So it will be a extrema when it is if the I mean so in that so yeah, if the pixel at that center in that cube is greater than all the values in its neighborhood, right? So it should either be greater than all of them or lesser than all of them. So only if it is that case, then it is an extrema. So this function returns if it is an extrema. So if it is an extrema, then I do the next step, like the key point localization. So this is the key point localization step. So after this step, if that particular extrema is not rejected, then then the next step is to do the orientation assignment, where you compute the histogram of the gradients and histogram of the gradients. I'll go over this. So here you let me. So I would take the neighborhood of the key point and then compute the gradients at each of the location, right? So here we have taken a neighborhood of at each point, computed the gradient like the dx, dy at that position, and computed its magnitude and the orientation. So these vectors are also weighted by its like distance based on the how based on how far it is from the center of that key point, so which is the weighting factor. And you, based on what this orientation is, it is assigned an index, that is which bin it belongs to. So I would have like 36 bins defined, which is 0 to 360 degree divided, so it's 0 to 10 degree, 10 to 20, 20 to 30, and so on. So which bin it belongs to, so the number of bins is 10, right? So 10 bins, um, the whole of 0 to 360 is divided by 10 bins. So I identify which bin it goes to. So I keep collecting the histogram values by adding it with the gradient magnitude, which is weighted by the weight which is computed by the Gaussian. So once I do this, then I compute what is the orientation of the key point based on which is the maximum value in that histogram. So this is a class which is defined for storing all the elements of the key point. I think like its location, at what size it is detected, its orientation, and in which octave this key point was detected. So after this step, we would have got like returns all the key points, which also has its orientations detected. So CV2 has this library to plot the key points. So the key points have all this information like the orientation and the scale of it, right? So based on what scale it was detected, they've plotted this scale and the orientation of the interest points identified. But there are a lot of points which are not descriptive enough, right? So you can do that Hessian based thresholding to get rid of such key points. And in the last step, we compute the get the key point descriptor of the image. So to get the descriptor of the image, okay. So at every key point, I get first retrieve the image based on which octave it was computed from. So I get the Gaussian image. So I would have stored it in that key point class, right, where in which octave I computed that key point. So based on that, I retrieve its Gaussian image, and once we get the Gaussian image, I can compute its uh, like the gradient vectors at that particular location. I mean, in its So based on its location, I'm looking at a neighborhood here, right, of a certain width and height. So I look at the neighborhood. So that is what we're doing here. Based on its location, I identify its neighborhood, and in that neighborhood I would compute the gradient vectors at each location. Okay, this is not a very readable code. I don't know what. Yeah, anyway. So yeah, this is kind of a repetitive thing, exactly similar to how the histograms was computed for the the orientation assignment, right? So within each neighborhood you compute them, and yeah, and then get the whole descriptor. Once you get the whole descriptor, you can normalize it to the range 0 to 255, so that it is scale in invariant to the intensity of the image. Okay, I know I didn't do a good job with going over the code, and it's not really something very readable which I can explain line by line. You should, but you should be able to like debug through it line by line and understand it, I hope. But yeah, anyway. Okay, that's pretty much what I thought for the session. Do you guys want me, if you have any doubts, you can ask, or if you want me to explain something specific in this lecture, say in this week's lecture, I can go over it maybe.
Ma'am, I have a doubt in the image pyramids thing,
Okay.
but not in the shift lecture. The lecture before the shift one. So in where we try to uh, draw a histogram of a given key point in the image and try to find the maximum of that, things like that. So I don't get really like why are we finding this maximum and what are we getting out of that? So I'm not really understanding the intuition behind it.
Of why histogram and maximum represent something. Okay. Which it is in the shift lecture only, right? Okay.
No, in the previous lecture, the lecture it was where we talked about filter banks also.
In this one.
Yeah.
There's no histogram computation here, right? Is it there?
Yes, this one, ma'am. This histogram and we are finding the maximum.
Okay. Okay, so here what they're trying to do is, okay, I don't know exactly, but my understanding is that, so suppose like this is an interest point, but at what scale is it really a key point, right? That's what they're trying to identify by doing this automatic scale selection.
So, ma'am, how does it help in this scale invariant feature detection?
So, Harris corner detector is not robust to scale, right? Like what
Yes.
is edge in one image might not be an edge in another image. But if I scale the image, so suppose, yeah, like these are the two images I have. So it is an edge in, uh, it it is probably, it's a significant edge in this, yeah, in this image maybe, but not in this, right?
Yes.
Like because I'm looking at a very local neighborhood here, like it is a significant corner here, but when I'm looking at a larger neighborhood, it might not come out as an edge here, but it is the exact same location. So I will not directly in Harris corner detection, I won't be able to do this matching, right? But suppose I want to make it scale invariant, what can I do is, this image is that this first image is there, right? I can scale this image, like zoom it up. So I can scale the image. Scaling the image is equivalent to looking at larger neighborhoods, right? Around that pixel.
Yes, ma'am.
So, yeah. So at each scale, as in first I look at a very small neighborhood, then I look at a little larger neighborhood, and so on. So at different scales, I will compute its. So what do they compute here? The cornerness, right? They have that measure of what a corner means in Harris corner detector. So they measure that. What is that measure called?
Yes, ma'am. They are measuring the cornerness measure only.
They have that cornerness measure, right? So at each scale, they will measure. They get that cornerness measure. So here at this scale, so suppose I got some measure, and again at this scale I got some measure. So you keep plotting that. At some particular scale, where there at some particular scale, I would it would look like a corner, but not in all scales, right?
Yes.
So at some particular scale I get it. So suppose this is the scale at which it looks really has I mean identifies as a corner. So I keep changing scales and I plot this, and wherever I get the maximum corners, I call that is the scale of that particular key point.
Okay.
And when I have another so if I have another image, in that also I can keep changing its scale, and in some scale it would have a high cornerness measure, right? So I can
Yes.
rescale that both the images to that particular scale where it has the highest cornerness measure. By doing that, I have brought both images to the same scale. Are you able to follow?
Ma'am, but in both the cases, like here in the other image graph also,
Hmm.
the scale is different, ma'am. The peak is the peak scale, means the scale at which the peak is, we are getting the peak value, that is
Hmm.
different in both the images, ma'am.
Yes, it will be different, of course.
So
So it
then
will.
how can we get into single scale and compare?
So it will be different, but whatever that scale is, I can rescale that whole image to that particular scale, right? So in this image, maybe I'll have to, it is this particular scale, something like 3.89, right? But for this image, it is lower, whatever, some 2.5 or something. So based on what that scale is, I will reshape this whole image.
Okay.
So in this case, I will be downsizing the image. In this case, I might be upscaling the image. Understood?
Yes, ma'am.
So because I'm upscaling this image and downscaling this image, I brought it to a same scale where both of them identify as corners. So once I do that, then I can obtain its matching point. Uh, does that make sense? So if I have a corner detector which is not scale invariant, by doing by scaling the images and identifying at what scale it is actually a corner, I can then find the corresponding points maybe, but not directly. So this is kind of so whatever we are doing in SIFT, right, like where we are identifying the key points which are already robust by calculating the image like the image pyramid beforehand and then identifying key points which are robust to scale. Here it's the other way. So I have a location and then I search for the scale where it is a corner. Like at least did you get some idea of what is happening?
Yeah, ma'am. I got an idea.
Okay. Yeah, so rather than doing this, better way to doing it is actually doing image pyramid first and then computing the feature descriptors, right? So that's what changes from Harris Corner to SIFT. Any other questions? Okay, then if you have no more questions, I can meet next week. Were you guys able to follow the content I presented today? Do you have any feedback or suggestions? Okay then. Thank you everyone.
Thank you, ma'am.